Continuing from the previous video that we analyzed the covariance of least square estimator, in this video clip we would like to state one of the important results of a least square estimate. It also refers to Gauss-Markov Theorem, that the least square estimate has the best linear unbiased property, or we call in short BLUE. This property, okay, relies on the DGP y equals x beta plus e, and under the homoscedasticity of the noise. This is to say that the covariance of E is a multiple of identity matrix. All right, that all the noise from the all samples has uniform covariance. In this analysis, it's also without of lost generality to just assume that the covariance, the variance is 1. Okay. I mean, the proof can be just slightly modified if it's not equal to 1. We're gonna see that the best linear unbiased estimator property of the least square basically means that the covariance of beta hat least square is gonna be smaller than covariance of beta hat from other methods that is also unbiased, that is also linear and unbiased. So it's the best in this sense, it's the best in the sense that it has the smallest covariance. So to show this, we're gonna construct another linear unbiased estimator. When we say linear, it means that your beta hat can be described by a linear function in y. So we assume that, okay, beta hat is by. Okay. Now, because you're gonna construct beta hat that is also unbiased. So if beta hat is unbiased, it means that, oh, sorry, this is x. It means that, okay, your y is x beta plus e, right, from the DGP. And then you will see that this is b x beta plus expectation of e, which is 0. So in order for these to equals beta, because that shows unbiasedness property, it is required that bx equals I. Okay. So for any linear unbiased estimator in terms of b times y, it requires that that matrix B must be a left inverse of x, because it's multiplied with x on the left hand side and it gives you identity matrix. Okay. We can also show the same way, just like we did before, that when your beta hat is given by by, the covariance is going to be b transpose. Just use the analysis that we had before, the same way. Okay, and previously we have derived that when the noise is homoscedastic, the covariance of beta hat is going to be sigma square x transpose x inverse, right? But we assume that sigma square is 1 without loss of generality. So covariance of beta hat least square is going to be this term. We multiply with bx and is transposed on the right hand side, because that gives identity matrix. It doesn't change the fact that the covariance of beta hat least square is x transpose x inverse. Okay, now we're gonna subtract covariance of beta hat from covariance of least square. Oh, sorry, we're gonna subtract covariance of beta least square from the covariance of beta hat. This is any other linear unbiased estimator. Okay, so you subtract this. Just plainly subtract one from another, but then you recognize that you can factor out b and b transpose, and then you have this term in the blue, in the pink box. Okay, now it gives us a very familiar relationship with what? You will see that this is the matrix we have seen before. This is called P. What is this matrix P? Totok? Oh, Totok maybe not here. Okay, probably, I'm not sure if anyone's here. City Park, are you still here?
Yeah.
Okay, what is P?
Orthogonal projection matrix.
Yes, this is a kind of orthogonal projection matrix. That has what property? P equals P transpose, P square equals to P. And because P is orthogonal projection matrix, we have property that I minus P is positive definite matrix. I hope that you review this property also. It's very simple. Like you have Y, right? Of course, if you project it, it's Py, right? So the magnitude of Py is obviously less than the magnitude of Y, right? After the projection onto the subspace, the norm of the projected vector must be less than the norm of the original vector. So we always have this property, and that is the same as to say I minus P is positive definite matrix. Okay, please verify what I said. Okay, so given that I minus P is positive definite matrix, then you would conclude that this guy is positive definite matrix. Of course, if you pre and post multiply by any rectangular matrix, it still preserves the positive semi-definite property. So the whole thing is still PSDF. So the results of this show us that, okay, at the end, the covariance of any other predictors, any other estimator, subtract by covariance of your beta hat least square, is always positive semi-definite. So it means that this guy, covariance of beta hat least square, has the smallest covariance. And that is the blue property of the least square. Okay, we can also talk about a more general case from the, this is again, let me emphasize that this is called Gauss-Markov Theorem. And recall that it requires homoscedastic assumption of the noise. We can talk about a more general case that what happens if we have correlated noise. So in this case, the covariance of E is sigma. Sigma can be symmetric and any PDF. All right, so the off-diagonal term may not be 0, which means your noise EI and EJ can be correlated with this assumption. We can also derive a blue estimator just by just rescaling the DGP equation. If your sigma is PDF, of course, there exists a square root of sigma that is also invertible if you assume that the covariance is PDF. So we assume that, okay, of course, not assume, I mean, there exists the square root inverse of sigma. And then you're gonna multiply the whole thing to the DGP equation. When you multiply this, of course, the reason why you multiply this because when you look at this as y tilde, the whole thing scaled, right? You can call this y tilde. You can call this the new regressor matrix x tilde. If someone turn on the microphone, you should turn it off. Okay. And E tilde is sigma inverse square root E. The reason why we scale by this particular metric is because now covariance of E tilde is going to be, covariance of E tilde is going to be sigma minus 1/2 covariance of E covariance of -1/2 transpose, but because I mean usually the inverse, the square root of sigma can be made symmetric. So this guy can be made symmetric. So I can just drop the transpose here. And of course, covariance of E is sigma, right? Which is represented by its square root, so that it is identity matrix. Basically, the reason why we scale the whole equation by inverse of the square root, just because we want to make E tilde to have unit covariance, so that we can exploit the property on the blue property on this slide. We already decorrelate the noise. Okay. Now let's get back. After we modify the equation, we rescale the equation. Now this is satisfy the setting in the previous lecture, the blue property. It means that based on this equation, the blue estimator beta hat would be given by x tilde transpose x tilde transpose x tilde transpose y tilde. These must be blue estimates. Okay, but that's not the same. That's not the same. That's beta hat derived from the scale equation is not going to be the same as beta obtained from the ordinary least square, right? They are not the same thing. So now I'm going to put back my x tilde and y tilde just from this expression. When I substitute everything, it's going to be given by the term in the box. You will see that sigma appears in the formula. This is called the generalized least square estimator of beta. This is when the correlated noise is not diagonal. When you know the covariance of noise, okay, the best estimate of beta, and it's best in what sense? It's best in the sense that this is the beta hat that gives the smallest covariance than any other linear unbiased estimator. And you see that you're going to exploit the noise covariance in the formula here. This is also similar to the weighted least square estimate we see previously. Because this is weighted least square solution, you will see that, oh, it's a special case when you use the weighting metric as sigma inverse. So it has a lot of reasonable explanation, because think about when your sigma is, just take a look at the special case, when sigma is what? Diagonal. Okay, it means that to get the best, to get the generalized least square, you're going to use sigma inverse, right? Sigma inverse, which is 1 over sigma 1 dot 1 over sigma n square. Is this the same as a weighted least square when the weight is sigma inverse? So it means that you penalize less when the ith measurement has a high variance. So if sigma I square is high, right, Wi, which is going to be sigma I 1 over sigma I square, would be less. Whenever the I measurement has high uncertainty, you penalize less on that ith residual. So that is the interpretation of the generalized least square estimate. Of course, in practice, you don't know the covariance sigma. The noise is never known, right? That's why you can replace it. If you have some information about the noise covariance, you can replace the formula here with its estimate. That is all about generalized least square and the blue property of the least square estimator.